Hello, everybody. I think we're ready to start today's webinar, the 24th webinar of the series of Latin American webinars. My name is Alejandro de la Puente. I'm currently a postdoctoral fellow at Carleton University in Ottawa, and I'll be hosting today's webinar for you. I'm very happy to announce that we're going to be talking about something that I'm really excited to hear about, because I haven't heard much about it, and it's about the inner 300 parsec of the Galactic Centre as seen by H.E.S.S. We're followed live by colleagues from around the world, people in Spain, we have people in Brazil, Sweden, Chile, and obviously France. And before we start the talk by Emmanuel, who I'm going to introduce in just 1 minute, I'd like to remind you that after the talk or during the talk, you can put your questions on the questions and answers that are in the Google Plus section of this webinar. And also you can use Twitter using the hashtag lawphysics. And we also have now a web page, a WordPress page, where you can follow us online and all the activities that we're actually doing. So today's speaker is Emmanuel Moulin, and he's currently a staff researcher at CEA-Saclay in France. He received his PhD from LPSC in Grenoble, France, and did a 2-year postdoc at CEA-Saclay before taking on his new position as a staff researcher. The title of his talk is The Inner 300 Parsec of the Galactic Centre as seen by the H.E.S.S collaboration. So with that, I'm going to hand you over to the speaker, and I really hope you all enjoy today's talk, and please don't forget to ask your questions right afterwards. Thank you, Manuel, and here it is for you to start.
Okay, so let me first thank the organizers, and I'm very happy to present you what you can see of the inner 300 parsecs of the Galactic Centre with TeV gamma rays with the H.E.S.S observatory. Okay, so you can hear me well?
Yeah, everything is actually it's perfect.
Okay. So so this Galactic Centre region is has been observed routinely for more than 10 years with H.E.S.S for many aspects, and there are many science cases we can cover with these observations. And today I'm going to talk about the quest for cosmic ray origin with these observations. Okay, so let me first recap a few things as a short introduction. So all of us know, all of you know that we are continuously bombarding by cosmic rays on Earth, and they are mainly composed of at about 90% of protons. This is the main components of the cosmic rays arriving on Earth. Okay, so these protons, their trajectory is deviated by magnetic fields, in the interstellar magnetic field, and also of course the intergalactic magnetic fields. So what is interesting is that this flux of cosmic rays is measured over more than 10 order of magnitude in energies, and more than many order in flux. What we can see is that we have almost a power law extended over many order of magnitudes, and we have basically two regions in this spectrum. The low energy parts, it is basically cosmic rays of galactic origins, and the low energy comic ray up to the GeV at least, they are produced by the supernova remnants. On the far hand of this cosmic ray spectrum, it is commonly believed that these cosmic rays have an extragalactic origin, but in between, the origin is not clear, and this is, let's say, between a few 10 to the 15 electron volts 1 PeV up to 100 of PeV. So this region is called the CNI, and for this region, we need to postulate, or at least we need other galactic sources or population of sources to provide the required cosmic ray flux we observe. And this kind of sources we call Pevatrons, in the sense that these sources accelerate cosmic rays up to PeV energies at least. Okay, so proton, of course, they are accelerated at the sources, but deflected during their way up to the Earth. What is interesting is that the gamma rays can be copiously produced at or in the vicinity of the sources by both during proton interaction or propagation. And these gamma rays, at least at the galactic scale, are not deflected, and then they propagate up to the Earth as in straight lines. So in that sense, we can they point back to their source. This is the one main point. And with this detection of very high energy gamma rays, we can have the morphology of the gamma rays at the projection site. And these are useful, very useful probes to look for the accelerated particle of the sources. Okay, so just in one sentence, what is interesting is that these gamma rays, they are very effectively produced through electromagnetic or electronic or hadronic interactions. And what is interesting there is that they can be effectively detected in the detectors by spaced or ground-based instruments. Of course, they also effectively interact with matter or radiation or B fields during their travel up to the Earth. So even the information they contain very important information about the acceleration processes, but they can arrive to us with some distortion. So to track these sources of PeV cosmic rays, these Pevatrons, there are basically three main channels. We need, of course, gamma rays in the 10 to 1000 TeV energy range. Also, neutrinos are effectively produced in case of proton interactions, so they travel directly unaffected up to the Earth, so they are a very useful probe. And there are some secondaries, I would say X-rays produced by secondary electrons during proton interactions, and these X-rays can carry out significant information also to PeV cosmic rays. So for the detections, so the gamma rays, we all know that they are detected with kilometer square array multi-TeV ground-based Cherenkov arrays. The neutrinos, they are detectable with some difficulties, but they are detectable with IceCube or Kind3 nets, and they carry also unambiguous signatures. And we have also, as I said, the X-rays that are produced by the secondary electrons, and in case of very high magnetic fields, these X-rays are produced simultaneously to the gamma rays because of the very strong synchrotron losses in case of very high energy environment, which is the case of the Galactic Centre. So they are produced basically simultaneously to the gamma rays. Okay, so in order to track for Pevatrons, cosmic ray Pevatrons, with the gamma ray measurements, we need to demonstrate that these gamma rays are produced through hadronic interactions, and that the parent proton spectrum can extend at least to 1 PeV in energy. So, but what we can see is that these protons, to allow for the gamma ray observations, we need targets for these very high energy protons. So this target can be matter, radiation field, or magnetic fields. So a target is required for the production of gamma rays. So, and one interesting target is the gas clouds that are, so let's say we can call them like barometers of cosmic rays. So these gas clouds are very useful in that case, and one thing which is important is that the gamma rays emissions coincide with the target material, the gas, but not necessarily with the primary particle accelerators. So in that case of proton-proton interactions, the kinematics of the process of the inelastic scattering of energetic protons on proton in the gas, in the interstellar gas, tells you that the gamma rays is about 1/10 of the proton energy. So what we need to detect in gamma rays is energy, gamma ray energy up to about 100 TeV. Okay, so what I just said can be is presented in this sketch. So what we can see is that protons are accelerated and can diffuse in the vicinity of the source, and in the case they eat gas, they can produce gamma rays and neutrinos that travel directly to the Earth. So this is an example of the spectrum of the broadband energy spectrum we can expect. So you can see here the gamma rays, the neutrinos, and the X-rays I just talked about at much lower energies. Okay, so now just a few slides about the detection techniques. So these gamma rays produced as they enter in the Earth's atmosphere, they interact very efficiently, and they produce an electromagnetic cascade. And the Cherenkov and the charged particle in the shower produce Cherenkov light, and these Cherenkov photons can be collected on mirrors. The light pool of the Cherenkov light is about 100 meters in radius on the ground. So if you pave the ground with Cherenkov telescope, you can collect and even have multiple images of this shower in your telescope. So the Cherenkov light is focused on the cameras that are the focal plane of the mirrors, and this light flash is very short, in a pixel basically, in a pixel of camera with about 0.1 degree field of view. The light flash lasts about 10 nanoseconds. Okay, so of course there are many. The gamma ray showers are dominated by the number of hadronic showers, and just give you a sketch of what the gamma rays and the proton shower look like. And what we can see is that here the gamma ray shower is much more concentrated along the longitudinal axis, and the protons is much more spread on the lateral axis. This is due to inelastic interactions, and IPT particles are produced in this kind of shower, and this creates sub-electromagnetic showers. So this is what you can see, for instance, for these two showers in Cherenkov flight on the ground. And what we can see is that for the gamma rays, you have more or less a light pool, a circular light pool. In case of protons, you can see many sharp showers on the ground. Okay, in the camera, what it looks like? So you have the hadron light event. So given the multiple sub-shower, you have different clamps in the cameras. For the gamma light, we have a kind of ellipsis topology in the camera. Muons that are also copiously produced from hadrons or interaction gives you circles, so they can be easily identified. So the discrimination at the camera level is done in the shower image in the camera. On their topologies, you can calculate moments of the image in the camera, for instance. And if you have a multiple image of the same shower in different camera, it helps you a lot to discriminate against background, and also to improve the reconstruction of the particle direction. So in that case, what you can do is that you can compare your recorded image to a database of image, and through a maximum likelihood procedure, you can recover the best parameter of any showers, energy, direction, and pack parameters, and so on. So on the analysis level, you can make a cut to separate your sample into gamma-like event and hadron-like events. Of course, what you can see on this slide, on the plot, you can see that you have still some contamination of background event in the signal sample. So to fight against or to remove this residual background there are several techniques, but one is to use the on minus off type measurements. So in this case, assuming that the residual background is uniform, you measure the background symmetrically in the camera field of view to the center of the camera. So in that case, you can estimate the residual background which is in the on region from measurement in the off region. Of course, you can use large off region to have a very good measurements and reduce statistical uncertainty on this background level. Of course, it can work only if the signal region is it's lower in scale than the field of view of the camera. For any extended emission, which is at the level of the size of the camera field of view, this kind of measurement doesn't work, and it automatically subtracts any extended emission. Okay, so now the H.E.S.S experiment is using this technique, and it works well since more than 10 years now. And the H.E.S.S experiment is, you may know, located in Namibia, and it consists of two phases. The phase one is composed of 4 telescopes of 12 meters in diameter with field of view of 5 degrees and high granularity camera with more than 900 photomultiplicators. And the energy threshold for zenith angle observation is about 100 GeV. The angular resolution per gamma rays is better than 0.1 degree. Energy resolution is about 15%. It works fine since 2003, and since 2012, one additional telescope is present at the center of the array. It is a big telescope of 20 meters in diameter, a field of view of 3.5, and a camera of more than 2,000 photomultiplicators. It aims to reduce the energy threshold down to several tenths of GeV at the price of degraded angular resolution, about 0.4 degree at 40 GeV, and it works since 2012. In parallel to that, there are also the upgrade of the S1 cameras, but what I will present in the following would be only result from the phase 1 of S, meaning only data taken with the 412-meter telescope. Okay, so we are detecting many sources in gamma rays, and what we call Pevatrons, since the gamma rays are produced up to TeV energies, and so far we have more than 170 gamma ray sources detected between 50 GeV up to 80 GeV, and each source is a particle accelerator. So this is a number of sources. You can see that it increased quite a lot, and since 2005. So there are many accelerators with related to many different sources: pulsar wind nebula, starburst, AGN, etc. One thing which is important with S, and it is a big contribution of the S experiment, is a scan of the galactic plane, and about 77 sources have been detected in the galactic plane surveys with S since the beginning. Okay, but about the Pevatrons, so there is so far no Pevatrons. Even what we think to be the main supplier of Pevatrons, the supernova remnants. All the supernova remnants we detect so far with ground-based Cherenkov telescope does not have the required features to be robust Pevatrons. For instance, the well-known supernova remnant RG 7013 is a very bright supernova remnant, but has a cutoff at TeV energies or so. So it cannot accelerate efficiently up to PeV, the protons up to PeV energy, since the cutoff in gamma rays it has about a few TeV. Okay, so the Galactic Centre region is very interesting for H.E.S.S, since we can see this region a large amount of hours during the years under low zenith angle, so it is very good for the energy threshold and the sensitivity. But this region is very crowded, as you may know, so there are many sources, SNRs, pulsar wind nebulae, and for instance, in the radio map, you can see here, there are many structures. You can see, for instance, some supernova remnants of molecular cloud, you can see, and even some arc feature. Okay, one important thing in that region is that it contains giant molecular clouds, which is called the central molecular zone, and this is massive structures very rich in gas, and this is about 10% of all the gas in the galaxy. So it's a huge concentration of gas in that region. Okay, so it's a very effective target for protons, for instance. Okay, so the Galactic Centre seen by H.E.S.S in 2005, you have two bright point-like sources you may know heard of. So the central emission is SG1745 minus 2290. So this source is still unidentified, so we don't know exactly which is the counterparts of these emissions. And we have the G09 that have been detected also. Further observation of the central emissions of G7014 revealed high energy cutoff in this on the spectrum, which is preferred of our power law by significantly prefer over power law, and the cutoff is at about 15 TeV. So it is a strong emission, about 10% of cloud flux, point-like, and so far we did not detect any variability. The flux is about constant. We detect about 1 gamma per minute. So about the position of these sources, the precision measurements is that now we are able to exclude some counterparts in the vicinity within the 10 parsec regions. And for instance, the supernova remnant Sagittarius A East is excluded at more than 5 sigma, and counterparts that are the viable counterparts are the supermassive black hole, the P-win, which is marked with the black triangle, and also a spike of dark matter. So, subtracting these two point-like emission, what we detect in 2005 is a diffuse emission, which is spatially correlated to the distribution of the density of molecular gas of the central molecular zone. And this points toward an hadronic origin of this emission, as we will see. Now, more than 5 years later, we have much more statistics in these regions. The previous map was done with about 50 hours. Now we have much more than that. We have more than 200 hours of exposure on Sagittarius A*, and we can do very detailed and spatial measurements of the diffuse emission. So this is the actual map, the H.E.S.S map, and below this you can see the angular distribution from Sagittarius A* of the emission. Okay, so in the map, in slide 31, this is the data set we have with H.E.S.S. It is more than 100,000 gammas in this map, and we have, this is the deepest exposure we have in H.E.S.S. And we can do very detailed map of the emission. Okay, so this is we have a complex structure of the emissions, as we can see, and if we zoom in, this is the map we had in these years, and you can see the diffuse emission in galactic longitude, in galactic coordinates. And so Sagittarius A* is marked with a star, and you can see in red the diffuse emission, which is extended and correlated to the molecular cloud distribution. This molecular cloud distribution is represented by the white contours that give you the density of clouds, basically. So what we did is that we measured the gamma ray luminosity in different regions that are the annuli and the circular region, black region, and we use the measurement of the cloud mass that are done independently, and with these two quantities we can go back to the cosmic ray energy density, since basically this is proportional to the gamma ray luminosity over the mass. Okay, so what we do is that we measure the flux of gamma rays in each of the regions and compute the luminosities, and given the mass measurements in each of the regions, we can compute the cosmic ray density. So for instance, in the slide 33, we can compute the cosmic ray density in the first open annuli, and we can do these measurements in all the black region where we integrate the signal. And what we can see is that the cosmic ray density we can measure is decreasing as we go further to the center of our galaxy. So this is what we can see here. And what we have is that we have a a decrease of the cosmic ray densities that allows us to locate the accelerator of PeV protons, of protons. And from the measurements, what we can see is that the 1/r behavior is preferred by the data, and significantly prefer over a flat behavior of the cosmic ray density, or even a 1/r squared dependency of the cosmic ray densities. So there are two conclusions: is that first, we can locate the accelerators. It is located within the 10 parsec of the Galactic Centre, and given the dependencies of the cosmic ray density, we can say that we have a continuous injection of protons with diffuse propagation on this scale. In order to fill all this central molecular zone, the injections must be continuous over more than about 1,000 years or so. Okay. Okay, so now we can also do some detailed spectral measurements, and on slide 43, on the right panel of the figures, on the figure on the top, you can see an open ring, and we extract the gamma rays flux from this region, and this is what is presented in the lower left panel. This is a flux of gamma rays as a function of energy, and the spectrum of this region is given by the red points. And what we can see is that the flux of gamma rays is a power law, a pure power law, and there is no sign of or hints of cutoff in the spectrum. And this is contrary to what we detect in the central emission, where we clearly see a significant cutoff. So, with the measure flux of the diffuse emission, which is the red points, we have a pure power law with an index of 2.3 and no cutoff up to about 50 TeVs. So with this, this requires that the parent proton spectrum should at least expand up to PeV energies. And given the quality of the measurements of the spectrum, the gamma ray spectrum, we can look for energy cutoff in the parent proton spectrums, in which sense we are looking at which energies the resulting gamma ray spectrum is deviating from the measurements. And this is what we can see. So we can put some lower limit at various confidence level on a possible cutoff in the parent proton spectrum, and you can see, for instance, that at 68% confidence level, the cutoff in the parent proton spectrum is 2.8 PeV. At 90% confidence level, it's about 0.5 PeV. Okay, so given that spectrum, what we can say is that we have some continuous injection over more than 10 to the 3 years, and if we calculate the cosmic ray power, it is about 10 to the 38 erg per second. So given these two things, which is new is that, and compared to the 2006 results, where we saw an excess of cosmic ray compared to the local sea of cosmic ray we detect in the solar neighborhood, is that we can now locate the accelerators. It is located in the 10 parsec of the Galactic Centre. What we can say now is that it accelerates protons up to PeV energies, and the acceleration is continuous, given that we can now sample the cosmic ray density in the 200 parsec of the galactic center. So given that, we have a robust detection of a cosmic Pevatrons. Okay, so but what are the possible counterparts of these accelerators? So of course, one of the viable counterparts is the black hole located at the heart of our galaxy, and in that case, we can see that given the accretion power of the actual accretion power of Sagittarius A star, and given the rate which is released in acceleration of high energy particle, we have a significant fraction of this accretion power which is released in acceleration of very high energy particles. So this is an important point, and also what we can say is what we can speculate is that Sagittarius A star may have been more active in the past, and we have some hints about this. For instance, if it is, we can see that there are, if the Fermi bubbles are connected to some outflows, it means that we may have on longer time scales, Sagittarius A star may have been much more active, and in that case, if it has been more active with an excitation power of more than 10 to the 38 erg per second, with continuous over 10 to the 6, 10 to the 7 years, this galactic center Pevatrons can explain most of the galactic cosmic rays about 100 TeV to PeVs, which is good. Okay, what are the other possible ways to look for these Pevatrons? What are the multi-messenger signatures of these Pevatrons? So, as I said quickly in the introductions, we have secondary electrons from pion decays, which produce prompt synchrotrons. Given the high magnetic fields, the X-rays are produced simultaneously to the gamma rays, and this is what given what we measure with H.E.S.S, this is a prediction of the flux in the keV range, for instance, and you can see this is on the top figure, and you can see the measured flux by XMM. So the predicted flux from this Pevatron in the keV is too faint compared to the diffuse thermal emissions. This is a black point on the figures seen by XMM. Another important channel for the signature of Pevatrons is the neutrinos that are produced via pion decays, and this is a predictions for various cutoff, for instance, in the proton spectrum, and you see that the predicted signal is close to the detection sensitivity of kilometer cube scale detectors. Okay, so I think I come to my summary. So the search for Pevatron, and I hope I try to convince you it's very important to understand the origin of cosmic rays, especially the galactic cosmic rays. We have several candidates observed with H.E.S.S, and the Galactic Centre region is one of the most important regions, and this is where we find the first robust evidence of of a Pevatrons. So given the risk data set, we saw a strong correlation between the gamma ray luminosity and the molecular cloud distribution. The correlation is not linear, and we have the first measurements of the radial cosmic ray density distribution in the 200 parsecs of the Galactic Centre. The spectrum we measure in gamma rays suggests that the black hole is likely the hadronic cosmic ray accelerators, which inject the particles over more than at least 1,000 years to PeV energies, and this is the first robust detection of a cosmic galactic Pevatrons. And the total injected powers is important, about 10 to the 38 tera per second, which is much more than the volumetric luminosities, for instance, of the Galactic Centre. So now the speculation is that if Sagittarius star has been more active in the past, it could explain much at least most of the cosmic rays in the near regions between 100 TeV or to a few TeVs. So there are other candidates that may be viable Pevatrons, and there are S analysis ongoing. And these Pevatron searches in the Galactic Centre region, there are key science projects for the next ground-based gamma ray observatory CTA. Okay, so with this region, S is able to cover a vast number of science cases. We have a very rich data set accumulated over the last 10 years. We can, of course, we have a detection of a Pevatrons. We have diffuse emissions, large scales, a variety of sources emitting at VHE energies. There are possibly outflows in this region, and maybe the base of Fermi bubbles. And of course, this region is also important for dark matter searches. Okay, so this is my last slide. I think I'm in time, or almost. And I leave you with my summary. Thank you.
Thank you so much, Emmanuel, for the very interesting talk. I'm going to open the floor for questions. Please don't forget for the viewers to submit your questions through questions and answers in Google Plus, and also through Twitter via the hashtag lawphysics. Sorry. So I'll take questions right now. There's a couple of questions already on the questions and answers, but I'll go with the questions on the floor first. So, anyone? Roberto, we cannot hear you.
You can hear me because I was mute. Okay, sorry. I like very much your talk, Emmanuel. Very nice. So I have a question regarding with dark matter. If it, I mean, kind of, it's likely that the source, this Pevatron, is the Sagittarius A, but is there a way to ensure that is, for instance, the Sagittarius A, or for instance, a kind of exotic source like PeV dark matter decay that is quite lately have been used for to explain these ice cube neutrinos at PeV, or I don't know if it was.
Yeah, of course, some PeV decaying dark matter would produce some extended gamma ray emissions. But here we have some strong correlation of the signal with the target material. So in that sense, I would say it is a conventional explanation of the diffuse emission we see in gamma rays. I cannot exclude that there is some contribution of more exotic things, such as taking dark matter, but yeah, and also in case of taking, yeah, you need, as you mentioned, some very heavy dark matter, which is possible, of course, but yeah, I would say we have some, yeah, we try to argue that this is the most conventional explanation that produce most of the signal we detect in the gamma rays. So yeah, yeah, this is what. Of course, we will have much more exposure in the next year with H.E.S.S and with the advent of CTA in that region. And what we want at the end is to detect the cutoff in the diffuse emission. And the study of, for instance, the energy cutoff in gamma rays, a detailed study of the energy cutoff in gamma rays with very good energy resolution may help you, for instance, to distinguish between some dark matter interpretation or more, let's say, cutoff in the proton injection spectrum, for instance. Also, you can think of long-term variability studies of the diffuse emission, and if, but quite long, if there are some different activity of Sagittarius A star, you may see some variability in the cutoff. But yeah, I would say that the one important thing is to detect a cutoff in the diffuse emissions and to measure very accurately the shape of the cutoff in the energy spectrum. That will be my yeah, something important for the next years. I hope it answers at least partly to your question.
Yeah. Now it's a little bit more, I mean, it's clear.
Okay, I have a question.
Go ahead, Herman.
I have a question regarding, well, also the data, because as far as I understand, there is no H.E.S.S data in this analysis.
Exactly, yeah.
Will it benefit at some point of H.E.S.S data incorporation here?
Well, what is important is, of course, the whole gamma ray spectrum, from the low energy hand to the high energy hand. So in that sense, you may want to have S2, but what drives the results, what happened in the highest energies of S2. With S2, you expect more flux sensitivity, but given the very large photon statistics we accumulate with S1, it will take some time to, even if we expect higher sensitivity with S2, it will take time to get the sensitivity we have with S1.
There is a question from the questions and answers at Google Plus. First, he says it's a very from Marco Santander. Very nice talk. Can you explain what gas density measurements and radial profile models you use to derive the CR density?
Yeah. Okay. So the mass measurements in all the integration region is a crucial measurements, and there are substantial uncertainty in this measurements. And it is accounted in the error bars we see in the density distribution of cosmic rays, but the mass measurements is at about a factor of 2 uncertainties. So to probe the density in this in this molecular clouds, we use the CS line measurements with some transition. So this is based on the CS measurements, and also we test. We also compute the mass measurements using other tracers of the gas density, such as CO or HCN, and using this the mass measurements with other tracers, still the 1/r behavior is significantly preferred over the other dependency of the radial profile. So yeah, this is it enough to answer, or do you want more detail? Of course, it was kind of request to use different tracers for the mass estimate, because they are biased in each of the tracers, so they are not probing, for instance, the same density range, for instance. So it was very important to use and of course the density within the clouds is not homogeneous, but we don't know exactly how much the clouds are clumpy, for instance. So it was crucial to confirm the robustness of the density measurements with other tracers. But basically, the mass measurements is within a factor of 2 uncertainties, and is accounted in the error bars.
I see. Yeah, he actually he got the answer, and he thanks you for it. I think there's another question from here from Miguel Angel, or not?
Yes, I actually have one. So very nice stuff, Emmanuel. I actually have a question regarding the cutoff that you mentioned. I was wondering if there are any expectations from models for the this central galactic source. Where should we expect the cutoff, if any? Or I mean, are there any estimates about that? Are also the observations compatible with what the people thought it would be? Can you comment on that?
What would be what we expect, for instance, in the cutoff of the proton spectrum? This is what you mean? Or,
yes.
Okay. So of course we don't know. At least we don't want. If we want power law acceleration up to PeVs, so to have some efficient production of proton at to this PeV energies, we don't want cutoff in this region. But formally, of course, there are some cutoff somewhere, and we want to measure it. But I'm not sure if there are not strong. There are no prediction basically, because we see that there are PVs, so we need some particular acceleration to be efficient up to this PV energies. We parameterize this in terms of a cutoff in the energies. So meaning that we don't want a significant decrease or loss in acceleration efficiency in the PV, basically. But there is no prediction of this cutoff.
Okay.
In the proton.
So what's the main limitation in your? I mean, when you make the measurement at the highest energies, it's just a statistical limitation, like statistics. You run out. Okay.
Yeah, basically we are in the statistic limited regime.
Mm-hmm. So I guess with CTA, all that will be probably better too, no?
Yeah, we will expect better, much more statistic with CTA, and And I think with S it will be difficult because now we are fighting with the systematics also in this region.
Yeah.
Thematic of the background is very is very difficult. So this is now I would say that this is not only we could accumulate more statistics in the next few years with S, but we will have to really understand much more in detail the background systematics at 10 TeVs, gamma ray energy, for instance.
Absolutely.
Very, very important and, of course, very difficult, but crucial, I would say.
Yeah. Thank you.
There is a question from the questions and answers section. It's from Diego Alejandro Restrepo, and he wants to know if you can explain how the center of the dark matter halo can be determined using this.
The center of the dark matter halo. Okay, so okay. Well, so all the dynamics in this region is dominating. So the gravitational potential in this region is dominated by the baryonic matters. Okay. So, for instance, the position of the black hole is located very precisely to coincide with the gravity center of the Milky Way, given for instance the star dynamics, the very close by star dynamics, and we can, given the velocities of these stars, we can this is Keplerian motion, which is measured, and we can accurately measure the position of the black hole. It is coincident with the gravity center. For the dark matter halo, if you assume sufficient relaxation time in this region between because dark matter and baryons interact at some point. So if the system is relaxed, in principle, there is no reason why the gravity center should not coincide. Of course, if the system is not relaxed, it might be the case. So it means that the gravity center determined by the baryons, by the stars, for instance, can be different from the barycenter of the dark matter halo. But given the relaxation time at the galactic center, it seems that it is relaxed. So I would say that there is no reason why it should be displaced, or at least, to my knowledge, some conventional explanation. We have a relaxed system. So in principle, the gravity center should coincide. I hope it answered partly to the question, but.
Sorry, thank you, Emmanuel. Is there any questions from here? Because there is one more from the questions and answers from Diego Alejandro as well. So I can go with that one unless.
Yeah, I have a very short question. I mean, about CTA. If Emmanuel, do you know more or less how many hours of observation requires CTA to improve largely this observation by H.E.S.S, or saying in another way also, how much time CTA will dedicate to this kind of searches, observation?
Okay, the Galactic Centre region and the inner few degrees of the Galactic Centre is a priority of the Consortium Observation Program of CTA. It is a key science project, a significant amount of observation is foreseen in that region. So we in the first years of operation of CTA, we expect about 500 hours in the few degrees of the Galactic Centre. So it will be a huge exposure, and so the exposure will be much more than the one of S in about in a few years. The exposure will be at least twice of S, and on the other hand, the sensitivity will be improved with CTA, the flux sensitivity. So we expect. I don't want to give numbers here because it deserves more quantitative determination. But I would say in several years, in about couple to 5 years, we hope to reveal the cutoff in the diffuse emission seen by H.E.S.S. But on the other hand, this region will be also very complex for CTA, because CTA will have to control the systematics very precisely in this region. Of course, given the energy threshold, we expect much more emission, and also maybe other contribution to the diffuse emission. So the future with CTA will be bright, I would say, but also it will be challenging and difficult to extract information, given we will have much more sources shining given the CTA sensitivity, and also we will have to work quite a lot on the system to control the systematics in this region. So
okay, I don't know, this is probably the last question that I'm gonna ask you. This is from Diego Alejandro Restrepo, and it's what is the key parameter to explain the PeV acceleration of hadronic particles? Is it magnetic field, event horizon, black hole size, etc.?
Okay. So the key parameter is that we want to have hadronic interaction. Of course, we can think of some leptonic models in the Galactic Centre, for instance, but the magnetic field is quite high, so about 100 microgauss. So in that case, the energy losses for electrons are severe. So in the sense that the electrons lose very efficiently their energy through synchrotron losses, for instance. And also, it is very difficult, given exactly this argument, to accelerate electrons up to 100 TeV, for instance. So this basic fact, I would say, challenge quite a lot some leptonic interpretation of the gamma ray emission in the Galactic Centre. So this is for the hadronic emission, this is what will be the arguments. On the measurements, is that there is a striking correlation with the cloud distribution. So if you want the electrons could not propagate. Let's say 100 TeV electron could not propagate over 200 parsecs. This is not possible in the galactic center environment. So you will need many leptonic sources, I would say. So, and this will require fine-tuning in the distribution of these sources, for instance. So that will be my answer to. So the real thing is that the measurements of the cosmic ray densities, which and the gamma ray measurements correlated with the gas density distribution, the location within the 10 parsec tells you that you don't have many astrophysical counterparts in that region, and yeah, in the 10 parsec region, to produce these energies over 1,000 years, only the proton accelerated in the vicinity of the black hole are viable possibility, I would say. I hope this helped. But
yes, thank you, Emmanuel. I think unless there is any more questions here, I think I have one really quick question because I haven't been able to ask one regarding IceCube. So IceCube is able to also have a sensitivity to these high energy cosmic rays, right? Through production of pions in the atmosphere, or did I get that wrong? And how complementary is the results against the results seen by H.E.S.S?
Of course, since it is pion interactions, it is very difficult. It is very easy to predict the neutrino flux from the GC Pevatrons. And so far, IceCube did not see any, let's say, extended emissions. But who knows? What we say is that it is within the reach of IceCube, given the flux we predict. But yeah, it's difficult for me to say more about the sensitivity of IceCube of this. It is within the reach of IceCube, I would say.
But these neutrinos will be much lower in energy as detected by IceCube, right? Much lower in energy than the gamma rays seen by H.E.S.S?
In principle, there is no reason for that, because if you, for instance, see one of my first in the introduction, for instance, let me just slide number 11. In principle, the number of neutrinos is about the same of the gamma rays, because the protons produce pi plus, pi minus, and pi zeros. So
yeah.
So in principle, the numbers of neutrinos they reach the same energies, and they follow closely. At least the index of the neutrino signal follows closely the proton spectrum.
I'm just thinking like a model builder, because a lot of models that have been proposed to explain these PEVXs at IceCube is, let's say, models of leptoquarks. Very high energy neutrinos produce a leptoquark in the ice, and then this one decays. So I was just wondering if you or anyone that you've talked to have thought of any beyond the standard model scenarios where these PeV protons can come from.
No, that would be. I did not think a lot about this, but that would be very interesting, I think.
Okay. Well, I think there's no more questions, and I want to really thank you for your time and for all the answers you've given us. So really, it was a really interesting talk, and I hope everyone that watched the webinar enjoyed it. I actually did a lot. Please don't forget to subscribe to the to the YouTube channel. You can see this talk all over again. It's going to be there forever, as long as the internet exists. And if you didn't have time to finish the talk, obviously you can finish it later too. So I really hope to see you for our 25th webinar, and thank you all for coming. And I'm going to leave you really quickly with, no, the end is not here, but well, I'm just going to leave you. But thank you very much, and you guys, everyone, have a nice day.
Thank you. Bye bye.